By the 1800s, cities were trapped in a cruel paradox. Picture a bustling metropolis, the heart of commerce, yet split clean in two by water. This wasn't just a hassle, it was an economic chokehold. The best bridge tech back then barely cleared 1,500 feet, about half the span of the Golden Gate. That left crucial urban arteries completely blocked. Consider the financial hit: lost trade, delayed shipments, severed communication, all strangled growth. Cities like New York, with the Hudson River over 3,200 feet wide, were literally cut in half. Ferries were the only answer, tacking hours onto every single trip. It was a systemic failure, not just a minor inconvenience. Connecting Brooklyn to Manhattan across the East River's 1,595-foot gap looked like an impossible engineering feat. Traditional truss and arch bridges, relying on compression, simply couldn't support their own massive weight over those distances. Their own structure was the problem. Imagine trying to move troops in an emergency, or rush perishables to market, with your city sliced in two. The chaos was immense. Lost trade revenue for New York alone amounted to millions each year. Even the era's showpiece, the Britannia Bridge, finished in 1850, only stretched 1,511 feet. That's about 5 football fields end to end. Impressive, yes, but still totally insufficient for truly linking huge urban populations across major rivers. Engineers threw everything they had at it, but timber and cast iron just lacked the necessary tensile strength. The sheer weight of the materials needed became a barrier, often collapsing under their own load before any traffic even got on. The dream of bridging these divides stayed exactly that, a dream. The challenge outlined on our screen wasn't just geographical, it was an intellectual hurdle, demanding a radical new approach. Early suspension designs, though promising, initially relied on iron chains, limiting spans to a maximum of about 1,700 feet. These chains, while strong, were incredibly heavy, contributing massive dead load. Subscribe if you seek engineering marvels. The breakthrough arrived with steel wire cables. Imagine having 16 types of eyes. You have 2. This material was not impressed. Early chain bridges, despite their ambition, often buckled under their own immense weight and dynamic loads. A maximum span of just over 1,700 feet proved a structural dead end. The solution emerged from an unexpected material: countless individual steel wires bundled together, offering unprecedented strength and flexibility where chains failed. Steel wire boasted a strength-to-weight ratio 4 times that of traditional iron chains, literally allowing bridges to become lighter and exponentially stronger. The Manhattan Bridge, completed in 1909, truly showcased this paradigm shift. Spanning 1,470 feet longer than 5 football fields end to end. Connecting these vast bundles of wires across chasms became the next grand engineering challenge, akin to stitching a giant, ethereal tapestry over a mile-wide gap. Early methods involved literally air-spinning wires, pulling individual strands across the gap one by one. A painstaking process. John A. Roebling pioneered the modern cable-spinning method for the Brooklyn Bridge, a marvel of 19th-century innovation. This changed everything. The Brooklyn Bridge, completed in 1883, features 2 main cables, each containing 5,434 individual steel wires, each as fine as a pencil lead. Subscribe if you think evolution has run out of surprises. It has not. Just like engineering continually finds new ways to defy limits. The Golden Gate Bridge's main cables are spun from over 80,000 miles of steel wire. That's enough to circle the Earth more than 3 times. The sheer scale is staggering, but the real marvel is how it's built. This wire isn't prefabricated. It's spun right there on site, strand by painstaking strand, a delicate dance over the churning water below. You have to picture this. A traveling sheave, a mechanical marvel, pulls 4 loops of wire at about 10 miles per hour. That's 8 strands a pass, faster than most people can sprint. Each main cable isn't one solid mass. Instead, it's built from 27 distinct strands, and each of those strands contains 452 individual wires bundled together with incredible precision. This meticulous layering ensures the load is distributed perfectly across the whole structure. Now, imagine doing that across a mile-wide gap. Each individual wire, just 5.1 millimeters thick, has to be placed with microscopic accuracy. This massive operation used enormous 60-foot diameter sheaves to guide the wire, spinning it in the air, strand by precise strand. Once all 27 strands were laid for one main cable, hydraulic compactors squeezed them into a dense, circular shape. It's like the bridge gets a super tight corset. Each Golden Gate Bridge main cable becomes a colossal 36-inch diameter pillar of strength, wider than a tractor tire. After spinning, these 27,572 wires are compressed into a rigid 36.5-inch cylinder, as robust as a skyscraper's column. Finally, galvanized wire is tightly wrapped around the compacted cable, sealing its 100,000-ton strength from the elements. Each completed cable can withstand 200 million pounds of tension, enough to lift 1,000 fully loaded jumbo jets. When the Golden Gate Bridge opened in 1937, 200,000 people walked across its deck on day one. But the real story began with cars. Nearly 10 million crossings happened in that first year. This wasn't just a statistic, it signaled a profound change. Just 20 years before, crossing the bay was a major obstacle. Now, with cars flowing and ferry services dropping by half in just 12 months, the region's landscape was shifting. Think of a new freeway opening up, slashing your commute from hours to minutes. That's what happened for tens of thousands connecting San Francisco and Marin County. The Bay Area's population jumped 25% in a decade as a result. Small towns exploded into busy hubs, all thanks to this newfound access. The bridge bound together towns, linking over 1 million people, about as many as lived in Austin, Texas back then. How could one bridge do all that? New businesses popped up, eager to tap into this wider talent pool and customer base. Property values in once remote areas like Marin County shot up 15% annually for 5 years straight, a pretty sweet deal for homeowners. And beyond its function, the Golden Gate Bridge immediately became a global symbol. More than 90% of people worldwide recognize it, a genuine architectural celebrity. Millions of tourists arrive to gawk at this engineering feat, pouring hundreds of millions of dollars into the local economy each year. Response times for emergency vehicles also improved dramatically, speeding help to people across the once divided bay. That's a direct, clear benefit to public safety. However, this population and traffic boom demanded huge subsequent investments. Building a mile-long road across water once took 45 minutes by ferry. But human ingenuity totally changed that game. Today, bridges like Turkey's Çanakkale 1915, finished in 2022, stretch the world's longest suspension span to 2.8 miles. That's almost 5 kilometers, or like lining up 45 football fields end to end. This leap in engineering scale is staggering. Take Japan's Akashi Kaikyo Bridge. Its central span alone is over 1.2 miles, a massive jump from the mere 500 feet early chain bridges could manage. Seriously, that's a 13-fold increase in how far we can reach. This efficiency drastically cuts travel time, allowing megacities to flourish, supporting populations exceeding 10 million. New York City, for example, grew by more than half in the decades after the Brooklyn Bridge opened in 1883, finally linking its separate boroughs. But these aren't just functional. They're pure architectural ambition. pushing materials and construction methods worldwide. Spanning continents and islands in over 30 countries, from Japan to Denmark, they literally pull distant places together. And they're built to last, designed for a century or more. The Brooklyn Bridge, still standing after over 140 years, is proof. Their colossal cables, made from enough steel wire to circle the Earth more than 4 times, boast incredible strength. Imagine hanging a whole pickup truck from a single pencil-thin strand, and it just holds. Engineers used to scoff at mile-long spans. Now, these structures are more than just roads. They're landmarks. The Golden Gate Bridge alone draws over 15 million visitors yearly, a testament to their economic and symbolic power.